Good morning, everybody. It's so exciting to be here, and thank you to Armando for this wonderful introduction, setting the scene, and it was great to hear about your own pioneering work and the pioneering work of so many people that led us to this amazing place we're at today. I also have to say it's so much fun to see so many people in one place, like in person, and to actually have a discussion that isn't online, so this is really great. I'm going to tell you about two aspects of software which I think will be critical for AI coding, modularity and legibility. I want to start out by being a grump and pointing out some problems with AI coding. Of course, you know, the state of AI coding is just absolutely remarkable, and I can't even believe myself, to be honest, when I use AI coding tools, even when I'm using ChatGPT, just how good this is. And it's in some respects nothing short of a miracle. And the benchmarks seem to show that. You know, there's a benchmark called SWE Bench, which was a benchmark for realistic coding problems, where they took thousands of basically issues from real Python repositories, presented it to LLMs and asked them to solve it. And the results are absolutely stunning, and they have a leaderboard that rates the LLMs according to how well they produce solutions. And this is just one example of the sort of many remarkable things that LLM coding can do. It turns out, however, that things aren't quite as good as they're sometimes claimed to be, and that there's a little bit of hype behind some of these things. So this one in particular I find very interesting. A study done at York University, actually by a master's student who just published his thesis a couple of months ago, looked very carefully at this SWE Bench issues and asked the following questions. If we look at these patches, right, how many of these patches are actually for issues where the person writing the issue described in the issue itself what they thought the solution was in the code? That would make it pretty easy, right? Well, it turns out about a third of them. A second question was, how many of these patches were deemed correct in the leaderboard assessment because those patches passed a test, but actually broke something else? That was about another third. And then they asked the question, well, you know, these LLMs have been trained on a lot of stuff. Maybe these LLMs were trained on these repos themselves. So what if we ask which of these issues were not present before the training cutoff? And it turns out it was less than 1 in 10. And so remarkably, when you look at this, the resolution rate falls precipitously. My recollection from the paper is down to like less than 1% for GPT-4, which was one of the leaders. So in summary, what this means is that LLM-based coding assistants actually often suggest code that doesn't work, and they break existing functionality. You will also have, of course, heard about this remarkable study that was done by the Meta study that was done last July, where they paid a bunch of programmers in an essentially a randomized control trial. What was interesting about this was they asked them to predict how much the use of AI would speed up their coding. They actually asked different people, not only the developers, but also machine language experts and economists. The economists were the most optimistic. They thought there was going to be like a 40% speed up. The ML experts a little bit less. The developers, you know, we're a cynical crowds. I'm sorry, thank you. It's probably lucky because I was insulting economists. Economists were the most enthusiastic. The developers themselves were the most skeptical. And interestingly, they were more skeptical after they'd actually used AI on this study. And of course, everybody knows what actually happened because this is very famous. The actual speed up was negative, and the use of AI actually slowed the programmers down. It's not really clear why this is the case, but there's lots of interesting anecdotal evidence that came out in that study with comments that you'll hear from anybody who uses AI coding tools. You know, made some weird changes in other parts of the code, randomly editing, all that kind of stuff. And so, you know, while this is a complete miracle, there are some problems here. Here's another rather interesting study that was done recently. There's a benchmark called Slop Code Bench. So Slop Code Bench is a benchmark that tries to actually measure how coding assistants do when you iteratively change the specification, when you ask them to do more over time, which is, of course, what happens in practice. And they did something fascinating. They measured the Gini coefficient, which is basically a measure of discrepancy. It's often used by economists to measure things like the degree of inequality in a society. And so they basically looked at degrees of inequality in the code base over things like the number of branches or the cyclomatic complexity or the lines of code in a function. And what they found is a dramatic increase in the Gini coefficient, which basically means, you know, in lay speak, that the coding agent is basically dumping everything in one method, that it's basically cutting and pasting, and that it isn't maintaining the structure of the code base. And there's also been an analysis by, there are so many of these analyses, you can find them yourself, but here's a study from an organization called GitClear that looked at a couple 100 million lines of code over the last 5 years, very interestingly, and they looked at a bunch of factors, including, for example, how much code is cloned. And what they found is, not surprisingly, in the last 2 years or so, when people have started using AI coding assistants, there's a lot more cloning and cutting and pasting, and a lot less moving of code, and a lot less refactoring. And so we might be actually approaching a bit of a sort of technical debt apocalypse, you know, in which the use of coding tools, unless we're careful, is going to lead us basically to masses of incomprehensible cut-pasted code. So what are we going to do about this? Well, I hear basically two approaches to how we're going to think about the use of AI. And this is a rather crude characterization, but nevertheless, I think, you know, many people sort of fall by their sort of inclinations into one category or another. So one category you might call automate the mess. And what that category says is, well, and the other is what I would call design for AI. So what does automate the mess say? It says, we don't need to change what we're already doing, right? Take our current practices as given, let AI agents loose on this mess, right? And because they're smarter than us, they're going to fix everything. So we're going to outsource our thinking to AI. And we're going to, in order to do this, of course, we're going to need to give these AI agents unlimited context. They're going to need to see absolutely everything. And there are even startups saying, you know, let the AI agents read our Slack channels. Then they'll really know what we're trying to do in our software development. Let them read our email, right? Next thing we'll have like electrodes on our brain, you know, so that they get our dreams at night. You know, that will be where the specifications come from. The design for AI approach says something very different. It says, no, if we really want to make these tools, you know, make the most of these tools, we need to rethink what we're actually doing. We need to make structures that are directly expressive of what we want them to do. And then what we want to do is not outsource all our thinking to AI, but outsource very tailored subtasks to AI, and to basically focus AI tools very intentionally on what we're trying to have them do. Now, as you've probably guessed, you know, I see myself as in the second category. To those of you who believe that, you know, letting loose, you know, masses of AI coding agents in parallel will actually find structure and will actually solve all our coding problems, I won't say that I know that that isn't the case. But what I will say is that if we follow the second approach, I think we'll be better off anyway, because when those AI agents get even better, they'll work even better in a world in which we have some structure. So what I'd like to do now is talk a little bit about what I think is wrong with our current practices and how we can actually fix them. So I'm tremendously excited by this because, you know, a few years ago when there was the sort of GPT, you know, appearance in, what was it, you know, late 2022, you know, a bunch of us were thinking, oh, you know, this is the end of everything we do. Like, no one's going to care about software design again. It's all AI, you know, sucking the oxygen out of the room. But I've actually come to think that this is a great opportunity for a renaissance in thinking about software design and all kinds of disciplines where we really need to think about what are we really trying to do. Because one way to think about it is if we're going to teach AI to do it for us, we're going to need to be able to articulate what it is we're trying to do, why we're trying to do it, and what form it takes. And that's kind of exciting. And I think it gives us an opportunity to do things right that we've been wanting to do for decades, but have never really persuaded anybody to do, because it always seemed we could avoid doing the right thing. And my contention is maybe we can't avoid it any longer. So what's wrong with current practices? So in short, I'm going to argue that what AI and human coders alike need is two things. One is modularity. This is nothing new, right? Which is basically structuring software into independent units. And we get all the things we know we love from that. Reuse, the ability to work incrementally on one piece at a time, division of labor. You know, one of the problems of fantastic AI agents is if they can write all over your code base, how on earth do you manage a team, right? Because if each member of the team lets them loose and, you know, and the AI agent is pushing commits that all conflict with each other, right, you're in quite a mess. So you need modularity to basically be able to have division of work, and of course, localized change. Now, there's another thing which I think we need, which is more controversial, and I should say a lot of these ideas are due to my student, Egan Meng, who's been talking about this and working on this with me for the last year or so, is that I think we need our code to be legible. And what I mean by legible is that the code directly expresses the behavior. So when you look at the code, what you see is what it does, right? That you know from looking at the code what it's going to do. And I believe that if you can do this, this is really going to leverage what's essentially the key ability of LLMs, which is, after all, to manipulate language, not to do elaborate reasoning about complex structures, but rather to manipulate language directly. And if we can do that, we're going to be able to make code that's easier to generate, understand, and modify. So a little bit about these two things and why we're not there now with modularity and legibility. First of all, modularity. So those of you who work in software development will know that one of the nice advances in thinking about systems and making them modular was the idea of microservices. And actually, this was most famously done at Amazon in the early days when Bezos had this great idea and said, look, you know, instead of like building some big, huge monolithic system that's going to be a big mess, let's make each business unit build a service to solve their problem, and then make that service available to other business units. That way we'll have nice modular pieces, right, that are freestanding, developed and supported by individual teams. And that was a fantastic idea. And there's been an explosion in basically the design of systems using these so-called microservices. The problem is this. This is actually a picture of some microservices for a British bank called Monzo. It's actually on a blog post in which they're talking about the security problems associated with this. But essentially, each dot is a microservice, and each edge is a dependence between two microservices. The coloring is by team. And so what you see is that the microservices are completely intertwined, and there are complex relationships between the teams. And this is what some people call microservice dependency hell. It's not a happy story. So we're not really where we want to be with modularity. Now, with respect to legibility, I recently watched a wonderful old video of Trygve Riska, who's the inventor of, and he's a well-known Norwegian computer scientist who sadly died a year or two ago, who's the inventor of some very novel ideas in programming paradigms. And he pointed out that this phenomenally successful, influential, and insightful and valuable book, the Design Patterns book, often called the Gang of Four book, makes an observation which Trygve describes as frightening. And I think he's right. And here's the observation. They say early on, an object-oriented program's runtime structure often bears little resemblance to its code structure. With such disparity between a program's runtime and compile time structures, it's clear that code won't reveal everything about how a system will work. And that, Trygve thought, and I agree, is a deep problem, right? And that if we want to make LLMs effective at writing code, we need to change things so that they're not like this. So just to give you a flavor, if you haven't seen this kind of code, here's some very skillful code. It's actually a case study example that's available free online as an example to support a very good book about domain modeling called Functional and Reactive Domain Modeling, in this style of development often known as domain-driven design. And this is what a lot of code looks like now, right? And this is actually, you know, this is very skillfully written code. It's for managing some trades and whatever. But I think what you'll notice if you just glance at it for a second is how overwhelmingly complicated the underlying structures are that are being used. In order, essentially, ironically, to achieve modularity, there are patterns and structures that make the code and what actually happens at runtime very difficult to understand. Okay, so what I want to do is I want to take a step back in trying to rethink this and ask two questions. One question is, if we're going to talk about legibility and we're going to talk about how code behaves, what actually is behavior? And then I'm going to address the question of what is modularity. So here's a way of thinking about behavior. There are three kinds of phenomena. There are individuals out there in the world that have persistent identity. There are relationships between them, and there are actions that happen, atomic occurrences. And we can think of them being related in the following way. The individuals participate in actions. The actions affect the relationships that hold, and these relationships connect individuals. So, for example, suppose we had a restaurant reservation system, right? So the individuals might be the users. There's Alice and Bob, who are going to be diners, for example. The restaurants, say, Mado and Rosetta. There are slots that can be reserved. For example, slot 1 and slot 2, imaginatively named. And there are restaurant reservations, like, reservation 1. And then there are relationships. So, for example, perhaps reservation 1 is a reservation for slot 2, right? And perhaps reservation 1 is a reservation by Alice. And maybe this slot that Alice has reserved is a slot for the Mado restaurant, and the time for that slot is 7:30. Okay, and the date for that slot is January the 20th, 2026, okay? So these relationships basically essentially give meaning to all these different individuals. And then we might have an action, like, for example, the action in which Alice reserves slot 2 and is given reservation 1. Or we might have the action in which reservation 1 is cancelled. Or the action in which that slot was actually created, presumably by the restaurant, when the restaurant decided that, the Mado restaurant decided that at 7:30 on January the 20th, they were going to have a slot available, right? And obviously there are more complexities, in a restaurant reservation system related to party sizes and maybe preferences over what table you want to sit at and so on. But this is the basic idea. Okay. Now, what is actually a behavior? Well, a behavior is basically a history of actions. So here's, which is sometimes called a trace. So here's an example. The restaurant creates the slot, creates another slot, one at 6 o'clock, one at 7:30. And then Alice comes in and reserves the, say, the 6 o'clock slot, maybe cancels it, and says, actually, I'd rather have dinner at 7:30, reserves the other one. And then Alice turns up, let's say, sometime later at the restaurant, and actually gets seated, okay? And we can think of the impact of these actions in terms of the relationships they produce. So at every point in this trace, there's some set of relationships that hold. So, for example, at this point, after the 2 slots have been created, right, slot 2 in particular, and there'll be similar relationships for slot 1, is for Mado at 7:30 on January the 20th, okay? And at this point here, after Alice has reserved, right, the reservation that Alice has, reservation 2, is for that slot, and Alice has that reservation, okay? Now, describing all of these behaviors, this is the problem of requirements analysis or problem description. It's, of course, a formidable task, right? And over the years, there have been many ways to do this. But, of course, the trick is to find some kind of structure in it. So how do we find structure in it? Well, the first thing we do is we identify some types. So maybe types of individuals, relationships, and actions. So we'll group the individuals into users, restaurants, slots, and reservations. And the relationships will become relations. So for example, is going to be a relation between the reservations and the slots. And then we'll essentially type the actions as well. We'll say whenever a reserve action happens, it takes a slot and a user and produces a reservation, okay? But these kinds of structures, and of course we can then specify exactly, the effect of every action in general terms on how it affects the relationships for the named individuals, right? These structures themselves are not large enough to achieve modularity, right? Just having these actions. These actions, if you like, are just like function calls. We need something larger. And so what's that going to be? So I believe that our leading contender over the years has been object orientation. And it's interesting because I think that object orientation is in some respects in retreat because people tend not to write purely object-oriented programs anymore, partly because they're not well supported by web applications. If you've ever seen object relational mappers, you'll know what I mean. Partly because of the success of relational databases. But nevertheless, if you look at code that people write, I believe it's deeply influenced by object-oriented programming. And I'm going to argue that that philosophical influence has shaped the way we think about code and has led us down a path which is damaging. So why is that? Well, what we really want to do is we want to think of some way to form larger structure. So what does that mean? Well, by analogy, think about music. Right? If you're a musician, you want to understand, a piece of music, right? Here's a piece of music that has 16 notes and rests in it, right? You don't, if you're a competent musician, which I should say I'm not, right? You don't look at all those notes, right? It's just like as when you read, you don't look at every letter in the book you're reading, right? Rather, what you do is you want something that's easier to recall and grasp in your head. So you say, you look at this, and if you're a musician, you say, well, that's just a C minor arpeggio, right, going up and down. And once I know it's a C minor arpeggio, I have it memorized, and I know what it is. It fits into a scheme. And the whole of musical composition is like that, right? It's not just that I have bars and arpeggios and chords and chord progressions. I have musical motifs. I have all these structures, right, which can be recognized essentially as patterns, right? And so the question is, what would these chunks be for software behavior? These mental chunks that psychologists identify as the way we think at a higher level, what would they look like? So for object orientation, the interesting thing is a very parsimonious philosophical move, which is to say we don't need anything else. The chunks will be the individuals themselves, right? So what we're going to do is we're going to take these types and we're going to call them classes. So for example, reservation will become a class. We're going to take the relations and they're going to become fields. And then we're going to take the actions and they're going to become methods of the classes. So we're going to produce a class like this. We're going to say that the class reservation, right, has, for example, a method seat in which you are seated for that reservation. And it has a state or some relationships that map that reservation to the slot it's for, the user it's by, and, for example, whether or not that reservation has been seated, okay? And this is beautiful because it means, for example, that this seated method can act only on this object, of course, updating that seated component. Now, this is the simple story of object orientation. The problem is it doesn't really work. And it actually turns out to be extremely complicated. And you need to be a very sophisticated programmer to know how to do this. And to give you a flavor of that, let me just give you a sense of why it's so complicated. So if we just consider this simple question, which class do you assign an action to? The problem, as we saw, is that many actions involve more than one individual, right? And so, for example, consider this action in which a reservation is reserved for a slot is reserved for a user producing a reservation. So this is about 3 individuals, right? So which class is it going to be? It could belong to any of them, right? If you know object-oriented programming, you know it's going to have to belong to reservation. But that's not at all clear. It turns out it's not even straightforward when there's one argument. What about canceling a reservation, right? Well, surely that has to be a method of reservation, right? Well, it turns out not, right? If it's the case that canceling a reservation is going to mean flipping some bit in the reservation, just saying now it's canceled, so we're going to remember the reservations, which is a perfectly good design, then canceling the reservation could be a method of the reservation. But if canceling the reservation actually removes the reservation, it has to remove it from something else, not the reservation. So it cannot be a method of reservation. It needs to be whatever it's removed from. What about which class you assign a relation to? Well, exactly the same problem. If we consider the reservation by from reservations to users, right, we should say, well, that should be in reservation to tell us who a reservation is by. But what if we want to ask the question for a user, which reservations does this user have? Well, then it should go presumably in user. And of course, the problem is this argument can't be resolved. So you often end up putting it in both places. And worse than all of this, and this is really, I think, the biggest hit to legibility, we end up having to invent classes that don't correspond to individuals at all. So if you consider, for example, in a simple user authentication system, an authenticate method, right, in which someone provides a username and password and you return the user, you might think this could be a method of a user class. But of course it can't be, right? Because what does authenticate do? It looks through a table of all the users and it figures out which user might match this username and password, right? And so this is going to have to belong to another class, which would typically in object-oriented programming be called users, right? So now this is really philosophically complicated. We have the user object, and we have the users object, right? And that's what you have to do. How about modularity? So I'm going to argue now that we've gone a little bit astray with modularity as well. So the idea I would claim for modularity is that you've got some code structure, and you want the code structure to match a problem structure in the world. So if there's some piece of functionality, let's call it A, you want that to map to some module in the code, and similarly for B and for C. And if you can do this, then you get the nice property that changes will be localized, right? That if I make a change to the function A, it will presumably be in module A, right? This is the idea of, this is basically Parnas's idea of information hiding, right? But unfortunately, two things go wrong. The first is what I call conflation, which is that you create modules that are actually mergers of different functionality, right? And now if you do that, we've failed to separate concerns. This module is now a kind of weird hybrid for this particular system. It's neither an A nor a B. It's application specific, so we probably can't reuse it. And it's going to be harder to code reliably. An LLM is going to be less able to recognize it. The other problem is fragmentation, which is that function A ended up in two different modules. And of course, if you do that, and this is a failure to do what's called encapsulation, you end up needing to coordinate the two modules, because the orange in A is going to need some of the orange in B, and that's going to produce a call, right? So this is a simple picture of modularity, but notice that this picture of modularity requires you to connect the problem world and the solution world. In current practice, we tend not to do that. In current practice, what we tend to do instead is this. We look at modules and we say, here's a system in which module A calls module B. That's not great. So what we're going to do is we're going to introduce an interface for module B so that the internals of module B are hidden, and now we'll make module A depend only on the interface. Now, this is certainly a big improvement, because what it means is that module A is less dependent on module B. But notice that from a functional point of view, and from the point of view of an LLM that needs to understand the system it's building, there's still a dependence. And A and B are not independent and cannot be built separately, because changes to B are likely to involve a change to the interface B as well. So, and if you think about this, this is why I think we ended up, particularly with an object-oriented setting, with very coupled software. So let me just give you a little example of what typically happens. Here's a program in which I've coded up, my reservation class and my slots and my slots. So this is my slightly awkward phenomenology, right? Which is that this is the class whose instances contain a set of slots, and this is the class for an individual slot. And now the way my reservation works is that when the reserve method is called with a given table and time, the first thing it does is it goes to the main program to obtain a reservations object, which, like the slots object, I haven't shown it, is some kind of object that holds a set of reservations. And it gets a reservation. It asks if there's already a reservation for this user at this time, right? Which would mean we're not going to allow them to make another reservation. If there isn't, we're going to go to the slots class, and we have to get an object containing these slots. So presumably we get that from the main program as well. And we're going to ask for a slot for this table at this particular time. And then we're going to go to the slot object, and we're going to mark it as unavailable. And if you just construct the dependencies between these classes, you'll see that we have a little picture like this, right? So basically, we have a complete entanglement. And this is what naturally happens when you write object-oriented code. Now, of course, I'm sort of caricaturing this. If you're a good programmer, at this point, you say, well, wait, I wouldn't actually do it like this. I'd use proxies. I'd use factories. I'd use observers. I'd use visitors, right? You introduce all these patterns that basically make the program illegible by producing layers and layers of indirection, one on top of another, in order to undo all the self-inflicted wounds that you started with. So concept design, which is the approach that I take, is a much simpler approach. And I should say, I sort of think of concept design as sort of old new. If you come away from this saying, wow, this guy thinks this is new, but this is all old, that's fine. These really are old ideas put together, I think, with some novelty. So you can think of this as a plea to return to some old ideas, or you can think of it as a new scheme. I don't really mind. So the idea is we're going to identify a concept not with an individual, but with an aspect of functionality that's complete in the sense that it makes sense alone, coherent in the sense that it doesn't mingle distinct aspects, and is purposive in the sense that it defines a unique purpose and will therefore likely be reusable because it's a piece that makes sense elsewhere. So for example, in our restaurant reservation system, we might have an availability concept and a reserving concept and a user authentication concept, a notifying concept, a reviewing concept perhaps, and a karma concept, and so on. And this reserving concept, for example, will manage the assignment of slots to users, and this availability concept will manage the availability of table slots. And there's also a hint here, right, which is that availability is going to be something largely that the restaurant workers will do, and reserving is going to be what the diners will do. And these concepts are going to be not only behavioral descriptions, but they're going to become basically like little microservices, right? And now with this point of view, it becomes much more straightforward to ask where the behavioral elements go. So for example, which reservation a slot is for is obviously related to reserving, as is which user it's before. Which slot a restaurant is at is part of availability, as is the table associated with it. And then likewise with the actions, creating slots is going to be part of availability, reserving slots is going to be part of reserving, cancelling them is going to be part of reserving, upvoting, for example, is going to be part of an upvoting concept. So you might ask, well, why does this help at all? So I want to tell you why it helps with the two problems that I pointed out. So why does it help with fragmentation? So what's going to happen is that we're going to actually change our code so that rather than doing what we would have done on a sort of object-oriented inspired thing, and this is basically parallel to the code I showed you before, in which there are lots of dependencies. So rather than having the reserving service call the availability service to find out which slot's available, which would produce dependencies and also of calls and of data, what we're going to do instead is this. We're going to rigorously separate them, and they're not going to know anything about each other at all. And then we're going to put them together with what I call a synchronization. This is basically just an event rule. And so the event rule is going to say, for example, that when a request comes in to reserve for a user a restaurant at a particular time, where some condition holds, and the condition is going to be that in the availability concept, there is a slot for the restaurant at that time with an identity slot. Then in the reserving concept, we're going to reserve that slot. And then in the availability concept, we're going to mark that slot as no longer available. And so what we've essentially done is sucked the coordination out of the services and externalized it. And as I said, this is not a new idea. This is essentially what event-driven architectures do. But this is being done here, I think, more systematically and more closely in line with the phenomenology. How do concepts avoid conflation? So here's the key idea. If you look at a typical object-oriented class, like, for example, a user class, you'll typically find something like this, right? And the reason is that you ask the question in object-oriented programming, what are the properties of a user? Or in terms of the phenomenology I showed you before, we take all the relationships that have user in them and we push them into the user class, right? But of course, if you think about this, each of these properties plays a different role. And it would have been better to have a class for users that was just about naming, that just had their username, one about authentication that just had the password, one about notification, which had the means of contact, one for profiling that had, for example, the display name and thumbnail images and so on, right? So that in fact, that what we would really want is to color the properties of the object, to deconflate it and break them out. And of course, that's exactly what we're going to do. So we're going to essentially, more relationally, but essentially following the same idea, we're going to take these services and make them independent and separate out the different state components. So they'll all know about users, for example, but user authentication will know that a user has a password. User naming will know that a user has a unique username. Display naming will know that a user has a display name, which is not necessarily unique, right? And the crucial thing is that in addition to encapsulating coherent aspects of functionality, these concepts are disentangling and deconflating the different functions so that they're able to store different properties. And then what we're going to do is we're going to coordinate them with these synchronizations. Now, if you're saying, this has all been done before, you're exactly right. Here are 3 of the more famous examples of people trying to do this kind of deconflation. in object-oriented programming. Perhaps the best known and most successful is the entity component system, widely used in video games. So again, you know, old new. This is an old idea. This idea of separation. It also goes back to some work I was involved with in, you know, the early 90s on view separation in specifications that many people were interested in at the time. And it's basically the idea that you can form different views of the state and behavior of a system. And so now what we're going to do is we're going to use this scheme to generate code, but now in a setting in which we have greater clarity about the mapping from the problem world to the solution world. And so the crucial thing is that now, because these concepts are fully independent, we can write specifications for the concepts and generate code from them completely independently. The concepts do not need to know about each other. Of course, when we come to write the synchronizations, because those synchronizations involve the concepts, they will actually need concept specifications. So the concept specifications are fed into the LLM to generate the synchronizations. We write the front end, and then we deploy the app. And we've done a bunch of experiments with this. We built a demo app in the style of this benchmark suite called Real World, which is a wonderful, it's a kind of medium clone that has been implemented in about 200 different frameworks. And we built this, and you won't be surprised to hear that since this app is a sort of conventional medium-like social media app with things like authentication, posting, favoriting, tagging, and so on, you don't need to write the concept specifications. You just need to give the LLM a background document telling it what the syntax of a concept specification should be, and it one-shots all the concept specifications and then implements them successfully. It turns out that the synchronizations are a little trickier. And I should say the reason they're tricky, and this is a topic for another time, is that if you actually look at the specification, the way this system works is that it actually conflates the concepts in the responses that come back from the web server. So for example, this is the response for get article, which is basically hydrated with all kinds of things, such as the user favorites and so on. So they actually haven't preserved modularity at the boundary. And this is quite typical of a lot of apps, and we think this can be avoided. But what this means is that you need quite an elaborate synchronization to do all this hydration. And we've also been teaching this in the class that I taught with Mitchell Gordon last fall, 6104. We presented this form of concept design to our unsuspecting students as if this was a completely standard approach to software development. They built their systems like this for their personal projects and then for final projects. Interestingly, we had them use a special tool that we developed, that my student Egon developed, called Context, which was basically a wrapper for Google's Gemini LLM, and gave very explicit control over context. Because when you build a concept, you don't want to waste your context on the rest of the code base. You don't need that, right? And so we built a tool that focused the context very closely. When it came to the front end, we haven't yet worked out how to build the front end, so we let them sort of run loose with Cursor. An interesting little anecdote, when they then came back to coding more on their back end, I will be completely honest and tell you that they wanted to use Cursor for that because it was so much easier. And Cursor completely screwed things up. It basically wrote all over the place, as you'd expect, and it actually broke the framework. In order to get the applications to do things correctly, rather than modifying the synchronizations and the concepts, it chose to modify the underlying synchronization engine in all kinds of bizarre ways. And 80% of the students actually did that. So there's a very interesting story there, which we're just still sort of taking apart about education and so on. This is a little snapshot of Egon's tool that basically provides you, this is in Obsidian, which is a nice markdown editing tool. You give it a prompt, it generates, or you write a concept specification. And these links here are the explicit context that you give at the beginning of the quote. And each of these markdown documents becomes like a GPT chat, like a thread of its own. And of course, it calls Gemini, generates the code, and we snapshot the code and also produce provenance links so you know what was generated at what time. We also built a little framework for them, which in addition to building these on top of Mongo and Dino, basically gave them a way to write these synchronizations using a very lightweight TypeScript library that also provides provenance and logging of all the events. So you get a nice kind of picture when you're trying to debug that says, these are the actions that happened in each concept. And a nice thing that I think was very helpful, we realized that as in that example I showed you, we could create a concept that represented the requests coming in from the user. And that concept can actually be generic and can fully encapsulate HTTP and routing. So actually, there's no need to write any routing code. You basically just write synchronizations of the form, when a request comes in for this action of this concept, do this and do that. So in summary, this is the idea. The idea is legibility and modularity, to take the functions in the problem space and the phenomena in the problem space, the individuals, the relationships, and the actions, and to map them very closely to the solution space. So the functional areas become concepts. The individuals become not encapsulated objects, but essentially object identifiers, foreign references, it's foreign keys in the language of relational databases. The relationships become relations of the state of the concepts, and the actions become literally just the actions of the concepts, which are essentially the API calls. So that's all I have. I'm be delighted to hear your thoughts now and to take some questions if we have a minute, and to continue the discussion after, if anybody would like to do that.
What if you implemented that restaurant reservation system as tables in a relational database, and all the actions were implemented as stored procedures? You know, what would that be an example of in your world of concepts programming versus something else?
So I think it would not be modular unless you impose some modular structure on it. So typically what people would do is they'd say, well, I'm going to have some vertical stacks with like, and each stack's going to have like, you know, a route, a controller, and some models for the fragment of the data model that corresponds to some relational tables. And when you think about what those stacks are, it would be typical to think about them in object-oriented terms. So you might have a reservation stack, which is going to have the reservation table in it, and a slot stack, and so on. And if you go down that path, and you can see this in the real-world examples, although you're using a relational database, you end up with a very object-oriented phenomenology and a lot of cross-dependencies and all the problems that I've been telling you about.
Thank you.
So I was wondering if formal concept analysis played any role in your work.
Not really. So the question is, did formal concept analysis play a role? In a sense, the word concept is ill-chosen because in formal concept analysis, it tends to be basically about building an ontology of objects. And my concepts are more behavioral descriptions. But it shares with formal concept analysis the idea of trying to encapsulate mentally recognizable units, although those units tend to be units of functional behavior rather than classifications of objects. My book has a lot more to say about that. Well, all right.
So my question will start out with a little bit of background, but about a week ago, a company, Factory AI, published a AI readiness report for repositories, and one of the things was that they said you need to set up linting, you need to set up automatic type analysis, you need to make sure that you have a good code review process and things like this. And it was set up as an AI readiness report, but in fact, it just sounded to me like good software engineering practices. And I largely agree, as somebody who's working on AI agents for software engineering, they work in similar ways to how humans do. But that goes into my question, which is, what do you think are the unique challenges and opportunities specifically for AI-driven development here? Can AI help us do refactoring into this sort of, shape more easily, or is it particularly important for AI where it was somewhat less important for human programmers?
So that's a great question. So first of all, I'll say that the first example you gave is lovely. And it's an example of, I've just written a little paper which is available on my website about LLMs in education. And one of the points I make is that I think there's a case to be made that LLMs are going to whip us into shape. that they're going to make us be organized because we won't be able to use them otherwise. And I think that's an example. In terms of whether AI agents can be used to sort of rediscover structure and to refactor code, I think that's possible. I'm not an expert in that. I think it's going to be very hard, but I think it is possible.
Thank you.
So just a comment, I think Alice really should have invited Bob to dinner that time. So that was probably a big mistake. But anyway, so you've described modular concepts that, some of which are known, some of which are new, but if there's code out there that an LLM can scrape and pick up these notions of modularity, then presumably you give it a prompt and it will more easily construct code based on those nice, neat modules. And this goes back to what is the purpose now of generating that code? You make the argument that you want the code to look more readable, more legible, presumably easier to maintain. Who's going to maintain it? If you go all the way back to Fortran and to all compilers, the idea was that you have this high-level language that generates a low-level language. When you use the low-level language, you work very hard to make it neat and clean as well as you could. But then when the compiler came along, it generated horrible-looking code, but you didn't care.
Right.
Because you're not looking at that code. It was nicely optimized, and your high-level language was neat and clean. So I guess the question is, what is a high-level language here for LLM-generated code?
So that's a great question.
Is it the prompt? Should we thinking about the prompt or whatever it is as the new high-level language, or is the purpose to generate code that then we can modify ourselves?
Right. In fact, our colleague Nir Shavit just wrote a blog post in which he argued that people like me who are concerned about the structure of code are like basically old fuddy-duddies, and that it's all going to go away. All the code will be generated automatically. It won't matter what's inside it because LLMs will be as reliable as compilers. I don't know if that's true. I'm a little skeptical. But even if it is true, I would say that I don't believe LLMs will infer our needs for us. And so I think there'll be an important role for expressing what behaviors we actually want. And so the language, if anything, then becomes the language of behaviors. And that's basically what this research is also focused on, which is how do you describe those behaviors in a coherent and structured way?
You used to, as an example, like hotel reservation services and other traditional object-oriented problems. But in my opinion, like the interesting software today is a small amount of code running data analysis, machine learning on massive amounts of data. And usually I haven't seen like object-oriented use that. So does your concepts apply to that case?
I don't know. Maybe not so well. I don't know. To be honest, I haven't tried it. It's interesting that you say that that's what you think the interesting application is. I'm not sure everybody would agree with that. I think there's a great opportunity for LLM software development to unleash the ability for all kinds of small organizations to make code, to make applications for themselves, where currently they have no such option. They either have to take something off the shelf or they have to pay a lot of money to SAP or Salesforce or Epic to make it for them. We see that even at MIT with a profusion of complex applications. So I think there's still an enormous amount of opportunity. In the whole low-code development world has been working on this for the last decade, wonderful companies like Airtable and so on. I think that's a great opportunity. So even if we can't deal with all these data analysis problems, I think there's a great opportunity. Whether this applies in the data analysis field, I honestly know. I think it'll be really interesting to explore. So it's a great question.
Yeah, thanks for the talk, and I especially like the separating from function, like translate to concept. And my work is more on robotics, so kind of like we want some task to be done, and then translate that to some formal description of that task, and even more maybe some optimization programs that can optimize for that task. Say I can design my robot differently, place so that it can better serve the task. Have you done this? I mean, optimization is a very powerful.
No, it sounds very interesting.
Yeah,
Maybe
yeah.
we can talk after about that.
Sure.
Very interesting.
Then one last question.
Yes, regarding legibility and modularity, my question is for whom? And what I mean by that is imagining humans at different levels of expertise, right? So someone who's just learning about a system. All of us here are familiar with restaurants, but what about like going back to like the biology or physics example? Like, so how, and there will be different code users at those different levels of expertise. How might that fit in?
Oh, that's a great question. I mean, I guess I am making the sort of somewhat philosophically dubious assumption that legibility is some kind of objective thing. The case for that, I think, is that there is an objective problem world, and that by and large, the users of a system have a consensus view of that problem world. At the same time, I think that in order to be a sophisticated designer and builder of systems, you often have to have an understanding of that problem world that will be too difficult to grasp for some users. So I think, for example, for a designer, the distinction between a reservation and a slot is very straightforward. The slot is, for example, what holds the range of party sizes. This is a slot for 3 to 6 people. The reservation says this is for Alice for Alice with a party of 3. Now, to us as computer scientists, that's a completely clear distinction. I would say, to the average person making a restaurant reservation, that would not be a clear distinction. And so I think that there'll still be a need. I think this is going to create a great need for designers who might not have coding skills but can operate at an appropriate level of sophistication in terms of understanding these sometimes intricate phenomena.
All right. Let's thank Daniel again.
Thank you.